you that Grace Yan is collecting those in the chat function. There are some there already, so please do feel free to add to them. The next presentation, one of the shorter ones, is going to be given by Francesco Ricciardelli. He's Professor of Structural Engineering at the University of Campania, Editor-in-Chief of Wind and Structures, Vice President of the Italian Association of Wind Engineering, a member of several committees within CEN, and he served on the Italian national standardization bodies as well. Over the course of his career, which isn't as long, I don't think, as Sven's, he's been the author of around 170 papers, most of which are in the areas of wind engineering and structural dynamics. He's going to talk about the calibration of code factors for climatic actions. In other words, beginning to look at how you, I believe, in how you put wind loads together with other sorts of loads as well. Francesco, you've told me you were there. Could I ask you to share screen, please? Yes, I can see you. Good to see you.
Thanks, Chris. Thank you very much. And good afternoon, evening, or morning, depending on where you are around the world. Let me try now to share my screen. Is it well visible?
We can you're sharing the screen, that's fine, but you need to start the presentation, of course.
Yeah. So, is it okay now?
That's fine. That's fine.
Okay. Yep. Thank you very much. So, well, Sven Dole clearly pointed out how we can relate the equation of loading from a code to the wind loading chain of Alan Davenport. And basically, he covered that part of the wind loading chain, that is the equation giving rise to the wind load. What remains to me to do in the little time that I have available is this part here of the wind loading chain, that is the calibration of the code factors, which is currently managed by the CEN TC250 SE1. Now, within that, project team was appointed that had the honor to lead on the interdependence of climatic actions. And basically, we had two tasks to fulfill. First one was, or is, to prepare a document with a probabilistic basis for the determination of partial safety factors and of load combination factors for climatic actions, which means wind, snow thermal actions, and atmospheric icing. And the other task, which is, I would say, a rather simple one, is to prepare European climatic load combination maps, which we did. And we prepared two sets of maps, one with the values coming from EN 1990 relevant parts, and the other one coming from the national annexes. But what I will do in the next few minutes that I have available is to look at what we are doing for our background document on the probabilistic basis for code factors. Now we have to start with wind velocity or velocity pressures, and we have a model which is included in the code. And we have to look a little bit more into detail on how the probabilistic approach is used here to evaluate the wind velocities or velocity pressure. In particular, we make the assumption that wind velocity is a distribution which follows an extreme value type 1, which is a Gumbel distribution. And therefore, we can get the relevant wind velocity associated with a given return period. Now, this is done fitting the type 1 extreme value distribution or the penultimate type 1 extreme value distribution to the available data. And we can use yearly maxima or yearly maxima or monthly maxima. I mean, we can do fitting using Gumbel, Norton, Blue or method of moments. And what I will show in the next slide is that the result that we get is very, very much variable if we change the method in which we fit the distribution. This is not the only methods that we have. We can also use method of independent storms or the method of Pickler's threshold or the spectral approach indeed. But as I said before, the first uncertainty comes from the way in which we fit the distribution. So what I'm showing you now here is little results that we got for the data, 50 years of data coming from the Ciampino Airport. And if we change the method of fitting, the reference wind velocity changes from 24.8 meters a second up to 25.9 meters a second. That's a difference of about 5%, which becomes a difference of 10% if you look at velocity pressures. So this is the first source of uncertainty. Now, the second step that we have to make is to combine the statistics of the wind velocity or of the wind velocity pressure with the statistics of the other factors coming to the load equation. The first thing is to combine it with statistics of the coefficient of pressure. What I'm calling stage one is the procedure of Cook and Main, which was set about 40 years ago, in which the fluctuations due to mesometeorological phenomena of the wind velocity are separated from the fluctuation due to turbulence. And the first are accounted for in the variability of the wind velocity, whereas the latter ones are accounted for in the variability of the pressure coefficient. So an assumption has to be made of what is the shape of the distribution for the pressure coefficient. And what we do is to choose also here an extreme value type 1 distribution. But then the question arises of what statistics of CP is to be chosen such that combined with the 50 years return wind pressure, it provides the 50 years return wind load. And very simply, it is found that the 70th fractile is the right answer to that. So it can be calculated straight from the parameters of the wind load distribution. But that magically applies only to the UK. In my opinion, if you do some calculations from other places around the world, you don't get exactly the same solution. But then there's another aspect, which is that the other factors appearing in the equation of the load or their variability have to be taken into account. So what I'm calling stage 2 here, which we can use is Monte Carlo simulation. So if we make assumptions on the distributions for the different parameters which we have in the load equation, and we make an assumption or we have a calibration for the coefficient of variation of this distribution, then we can make a Monte Carlo simulation and get the distribution for the wind load and use that for calibration of the load factors. But on the other hand, we notice that if we use crude Monte Carlo simulations, we don't allow for the duration of storms, which is the same thing of not allowing for correlation of events, which again is the same thing of not allowing for the spectral content of the load variation. So we can move to a further stage, which I will call stage 3, which is the reliability approach, which is used by course of practice. And in doing this, we have to select the probability of failure and accept the value for the probability of failure, or equivalently of the safety index. And then we have to select what we call a sensitivity factor, which is the factor separating the partial factor into a component which goes to the load and the component which goes to the resistance of the structure. And then out of that, we can calculate the partial factor. So just to show you how the way in which we do this affects the final results, I'm showing you an example. We selected a particular location, and we made the calculation for the ratio between design wind pressure to the characteristic wind pressure, which represents a partial factor on wind pressure. And in doing that, we got exactly 1.5, which is the value suggested by the current version of the Eurocode. Now, if we do the same thing, instead of accounting only for the velocity variation, we account also for the variation in the pressure coefficient, and that is, we use the method of Cook and Main, then this coefficient, the partial factor, increases from 1.5 to 1.6. Then we like to include also the variation in the other parameters which are in the load equation, which is the gust factor and the approximation of the variation we have height of the wind velocity. And then in that case, the factor increases in a range between 1.63 to 1.7, rather larger than the value which is given by the Eurocode now. And third, and I would say final stage here, is the one of looking at the not rather the action but the effects. So when we look at the effects, we have to combine the effects coming from wind loading with those coming from permanent loads. And in doing that, we also need to consider a specific structure. So the results that we can get are related to one specific structure. So the example that I'm showing here to you is a low-rise industrial building, a porter frame. We combine the wind load with the permanent load as a function of the ratio between the characteristic, which is the parameter heat, the ratio between the characteristic value of the effect of the wind load to the characteristic value of the sum of the effects of wind load and permanent load. And if we do the same exercise that I showed before, we end up with the partial factor of 1.65. So basically, the conclusion that I get to in this first thing is that We need to be very careful in the way in which we calibrate the partial factor on loads, because this is very much related to the way in which we model the components that appear in the equation of the wind load, and if we look at the effects and what are the effects that we're looking at. Second, and the final aspect that we consider is the calibration of the combination factors, which we use when one or when more than one variable load is applied to the structure. And the first question that we have to give an answer to is, are climatic actions correlated to one another? So if we take wind load, for instance, and snow load, which is the case of the example I'm showing to you now here, are they combined with each other, the maximum? Now, if you look at the blue dots on the top plots, you saw that for at least for the stations that we consider that indeed they're not correlated with each other. So we couldn't find a pattern between the extremes of the one and the other. And that was confirmed if we use some measure of the asymptotic correlation between the two parameters, which are those two parameters, key and key over bar. And in few words, if you let the probability tend to 1, by checking the value of these two parameters, you have information about the correlation of the two phenomena. And in particular, if the parameters tend to 1, then it means that there is some asymptotic correlation, whereas if they don't tend to 1, there isn't. And if you look at the results that I'm showing you here, you see that basically you can confirm that there is no correlation between, at least in this case, between snow and wind. Now, once this is set, we can use the standard approach, which is used in code calibration for combination factors, which is the approach of Fediboghes and Castagneta, in which the assumption is made that the reference average time for the different climatic actions, or in general for different actions, they are multiple of each other. Then it's possible to establish the joint probability of exceedance of the two loads, set design points for a given value of the probability of exceedance, and then calibrate the combination factor as those values that give the same probability of exceedance for the two combined load as that of the single load, if it's considered just a load. Now, assuming, as we said before, that the loads that we're combining, they're not correlated with each other, what we can use is the Turkström, which simplifies the calculation by looking only at the parameters of the loads to be combined, that is not looking at the parameters of the main load, the principal load. And it turns out that the combination factor, or the fundamental combination factor at the infinite state, is a function only of the coefficient of variation of the action to be considered, to be combined, of the target reliability, and of the number of yearly uncorrelated extreme events. And that latter parameter, that R parameter, is the most complicated one to choose in this calculation. Now, to conclude with, I would like to show you an example, an exercise that we made for Italy. We had data from Met stations in Italy, about 100 Met stations, so we could calculate the scale and shape parameter of both the parent and extreme value distributions of wind velocity. And out of that, we could, we found that the distribution of the parameters of the wind velocity were not the same at all stations. And we could establish an empirical CDF of the coefficient of variation for the wind velocity. And as we said, the psi factor is a function of the coefficient of variation of the load and of the wind velocity in this case. So we could also establish an empirical CDF for the psi coefficient. This is very nicely fitted by a normal distribution. It means that mean and median values, they're the same. And if we take that value, which is both mean and median value, we found that it turns out to be 0.54. So that was a way to calibrate it, at least on a limited regional area, which is that of Italy. Now, this accounts only for the variation in the wind velocity. If we add to that also the variation of the coefficient of pressure, and we again rely on the method of Cook-Lane, we found different results here, but it goes on the opposite direction as we found for the gamma factor, the partial factor, because in that case, the variability on the other parameters of the load equation, that is in this case of the pressure coefficient, increased the value of the gamma coefficient. In that case, the one that I'm showing you here, in this case, inclusion of other parameters that combine together in the equation of the load, that is in this case the pressure coefficient. In this case, the psi factor is reduced to get lower values, and depending on what is the value of the characteristic product for the pressure coefficient, we get values of the psi naught factor of 0.42 to 0.46. In this case, the reference value to be taken from the end 91114. The current version is 0.6. Thank you very much. I hope I've been able to say everything in my 10 minutes.
Thank you very much, Francesco. As with the other presentations, we'll take all the discussion at the end. So could I ask you to unshare now, please? And I will introduce the next speaker to you. The next speaker I have known for a long time. John Dora is a visiting professor at the University of Surrey, a visiting lecturer at the University of Birmingham, and the International Organization for Standardization's global lead on adaptation to climate change. I think John would be the first to admit that he's not a wind engineer, but he does have 40 years experience in infrastructure resilience and asset management. He's an advisor to CEN and CENELEC and works closely with the British Standards Institution. He chaired the committee that drafted the first ISO code on adaptation to climate change and is the chair of the UK's Infrastructure Operators Adaptation Forum. He initiated and led the first adaptation studies for the entire British Rail network, and recent clients include the UK Rail Regulator, the UK Met Office, UIC, which is the Worldwide Railway Organization, and the UN Economic and Social Commission for Asia and the Pacific. His talk is entitled Developments in Addressing Climate Change in Design Codes. Could I ask Francesco, please, to stop sharing, please? Stop sharing the screen.
Is it still shared?
Sharing. Could you just stop that? No, you're still sharing, I think.
Oh.
If you could stop the share.
I'm trying to do so.
Let's see if I can.
I'm not sure how to do that.
I'm stopping you sharing. Okay, I've done it.
Yeah, thank you. Sorry.
Could I ask John, please, to share screen? Hello, John. Nice to see you.
Hi, Chris. Good to see you, and thanks for inviting me to speak at this. This should be my slide on the screen now.
It is indeed, and we can see you and
With
hear
a bit
you.
of luck. Yeah, good. Well, again, thank you for inviting me to talk about developments in addressing climate change in design codes. It's something I've been working on for some time. And I've got some general material in this set of slides and some specific to do with wind engineering. But as we know, there are lots of standards bodies in the world, global impact with international standards, International Electrical Commission. Europe, we've got CEN, CENELEC, we've got national standards bodies, and I've got a list of a few there. That wasn't meant to be a comprehensive list, it was just an example of people that I know and people I work with, actually. We talk about sometimes horizontal standards at topic base that work across different sectors. Sometimes we talk about vertical standards, which can be sector specific. And infrastructure could be one of those sectors. And types of standards, management system standards, and we're probably all familiar with things like ISO 9001 on quality management systems, maybe less in awareness of 14001, which is environmental management systems. But we're very much into things like test methods and technical specifications like the Eurocodes, the structural Eurocodes. Resilience standards, I'm thinking of resilience, I'm thinking of climate change adaptation. This is just a list, an illustrative list of some work I did a few months ago for the Asian Development Bank. But you can see at the top left, you've got kind of like horizontal standards on adaptation. That's 1490 is the one I chaired the working group to develop. Risk management, crisis management of water utilities. And on the right-hand side, you've got sector-specific rail, waterways and ports, wastewater energy, and so on, in between a mix of different things like guidelines for planning, survival, urban planning, seismic design, and so on. So this is a list of all the sorts of standards that are around in terms of maybe high-level guidelines. What we're missing, I think, is some of the challenges that come from looking at long life standards like the structural Eurocodes, and also the use of standards. And organizations might use standards only if they have to. Legislation in Europe, we've got laws that say safety of structures is kind of aligned with the structural Eurocodes. So we've got that in Europe, and the structural Eurocodes used all over the globe. Some work I did a couple of years ago in Singapore, I asked a question about this new metro station, what design codes, and they said the structural Eurocodes. Similarly, a couple of years ago in India, they're building a new railway in India for freight, and there are 4 segments to it, but the northeast one that I looked at was about 800 kilometers long, and it was being designed and built to the structural Eurocodes. So these standards are there for a long time. The banks, the investment banks, like them being used, but they're all based on, when it comes to weather, these tend to be based on historic climate. And the climate is changing quite rapidly, as we can see just looking out the window. You know, we've got a bit of a cold spell in Europe just now. And people say global warming. How does that happen? Well, it's warm in the Arctic and things are changing. Things are changing rapidly. And the design life concept that's built into our design codes brings uncertainty issues. And perhaps I say here a reluctance to invest. How can you design something that's got a 50-year or 100-year design life if the future climate is uncertain and we're designing them with thermal or wind or snow loading from maybe 1961 to 1990 climate, which has already changed? So there's potential for locking in poor resilience into the lifetime of an asset, which is what I say here. However, there's a lot of developments, and I very much sometimes talk about the Paris Agreement, the United Nations Sustainable Development Goals, and how they kind of pushed governments across the globe to think about reducing greenhouse gas emissions, but also in the Paris Agreement, Article 7, we talk about adaptation to climate change, and that was a major driver in the UK and China pushing ISO 14090, which was published in the summer of 2019. But in Europe, a mandate from the Commission to SEN M526 was in support of the strategy on adapting to climate change. And the mandate to SEN was contracted to the Netherlands Standards Organization, NEN, and I'm a subcontractor in that work. And the mandate and the work that's going on is aiming to include climate change adaptation in standards with tailored guidance for standards writers, which is in draft just now. And a lot of it is wrapped into a proposal for a SEN technical report, which, as some of you may know, is a low-level standard, a technical report that will talk about how to incorporate climate data into standards as you redraft them or go through the review or in the new drafting process. TC250, the technical committee in SEN that looks at the structural Eurocodes, they're working on the next generation Eurocodes. So there's an opportunity there as well. But other design approaches exist. Now there's this thing called adaptation pathways, and it's about designing infrastructure and maintaining infrastructure with a view to what's going to happen in the longer term. And British Standards Institution is producing BS 8631. It'll be published quite soon, which takes up this topic, which can help to design infrastructure in a way that it can be adapted over its life cycle. And there's a good example going into 8631. It's been led by a colleague of mine, Tim Reeder. A good example going into 8631 about using adaptive pathways for the Thames tidal defences, the Thames barrier, and protecting London from flooding. So these are just interesting developments that are going on, all current. So the mandate, M526, what's it all about? There's a load of different organizations in Europe involved in this. And this is just a chart that I put together to try and get my head and a project team that's developing this outline for a technical report for SEN, a project team of which Francesco and Sven are part of. We're trying to develop in this work the outline for this standard. We've got a workshop in March, but the complexity, there are various Director General organizations in the Commission that have got a finger in the pie. There's a SEN mandate 515 to TC250 to look at climate into the Eurocodes, the working groups there. There's the Joint Research Centre, there's DG GROW, DG DEFIS, DG Klima, all looking at this. And the work I'm doing is TG1 JD, Outline for Technical Report, involving quite a few different organizations here as well. So there's a lot going on, but there's a lot of good information as well. Copernicus Climate Services are producing lots of climate data in their climate data store. There's lots of good information, and we need to draw that together. So thinking about wind actions, there's work in progress, looking at some questions. How do you produce a standard that will be around for what, maybe 10 years, with maps that issue values based on perhaps 30-year recent climate observations and look at future conditions? And Sven and Francesco have been telling me that these are things they're looking at, deliberating on. Maybe a national factor for future conditions down to the national standards body. That's what the NSB is here. And the other aspiration is to have a map for Europe. But how does that work with the politics of national standards bodies? These are issues that are being teased out. But the notion in the structural Eurocodes of having a static standard and allowing flexibility is something that's being built in, I believe, in the way the Eurocodes are being developed. Because the big thing that I know, having worked in climate resilience for nearly 20 years now, there are very good future projections. Climate change services, Copernicus Climate Change Services, pan-European. UK has its own climate projections produced in 2018. Highly granular, some of these things as well, going down to sub-kilometre granularity. But one of the things I do remember is that wind projections, of course, are very uncertain compared with the thermal and precipitation and snow loading Eurocodes. That's something we need to bear in mind. And when Sven earlier on mentioned that sometimes it's a challenge to think about climate change in wind design, I think that's part of it. But then again, I also think about the adaptive pathways approach that I mentioned a minute ago. And is there a way that we can build into the codes some way to allow users to use future data from reliable sources like Copernicus, like UKCP 18? If you go online and have a look across different providers of climate data, you can get some really good stuff, but I'm not sure that everybody works with the same sort of robustness and rigorous testing and proving of the data like Copernicus and UKCP 18 do. And of course, the Met organizations like Deutsche Wetterdienst and others have their own climate projections that could be used. So how can we allow users to choose to use future data, say 5 years time, when the Eurocodes are still static, maybe published 2021, 2022, but how do you use that in the future? We can find a form of words to go into the standard to permit that, I'm sure. So near the end now, everything seems positive in my view. From a couple of years ago, thinking that I was looking at some of the infrastructure standards, not the Eurocodes, as part of the mandate work, I was thinking we really need to look at the Eurocodes as well, and that work was going on. So factors for current wind observation derived data has been thought about. Flexibility has been thought about across the suite of Eurocodes. Better climate data is available up to the end of the century. Granular down to, UKCP 18, there's some good stuff down to 2.2 kilometre granularity. The mandate work, the M526 mandate work, as well as producing guidance for standards writers on how to incorporate adaptation into their standards. And that's part of the work I'm working with this project team, this workshop on the 17th and 18th of March. And also there's a guide by ISO on incorporating climate change into standards, which is already published. The tailored guidance for the mandate work will be published later this year by November. But of course, clients can always specify better resilience if they're guided in that way, compliant with existing standards. So when we think about infrastructure that's been built with a long life, it's having that conversation with the client to work out how can they be compliant with existing codes, but look at a better resilience over the longer term. The mandate work obviously helps with producing a technical report or an outline for that report on the use of climate information in the Eurocodes and in other standards. And of course, I mentioned 8631. If you Google 8631 and adaptation pathways, you'll find that it's just finished its public consultation process and will be published fairly soon. And just to plug, if you want to know about ISO 14090, this is in the PDF version that will be circulated. We're doing training on ISO 14090 and adaptation to climate change. But that's me. Thank you. And thank you again, Chris, for inviting me to present at this seminar. Cheers.
Thank you very much indeed, John. Again, as with everyone, could I ask you to stop share screen and we can move on to the final of the short presentations.
There we are.
Thank you very much. The last presentation, we move from Europe across the Atlantic to the USA. Donald Scott is a senior engineer with PCS Structural Solutions. He's got over 38 years of experience in the design, evaluation and rehabilitation of building structures. He was the principal investigator of the ASCII SEI pre-standard for performance-based wind design. He's chair of the SEI Code and Standards Executive Committee, chair of the ASCII 7 wind loading subcommittee, a member of the main ASCII 7 committee, and past chair of the NCSEA Wind Engineering Committee. He's a member of the SEI Board of Governors and the past president of the Board of Directors of the Applied Technology Council. His talk is entitled Latest Updates to the ASCII 7 Wind Provisions and Development of Performance-Based Wind Design Pre-Standard. Just before he starts, could I once again remind you that if you'd like to put some questions into the chat function, we'll put at least some of them to the speakers after the talk. Thank you. Donald, if you could share screen then, please. If he's there, there he is.
You see that now, Chris?
Yes, I can. I can see you now. See that now. Yep.
Thank you very much. We'll get started here real quick, and we'll try to not take too much time. I appreciate all of the presentations, and like I said, we've talked with Sven on the Eurocode on the wind standard there, and it's been great to have him in a few of our meetings. Currently, ASCE 7 is, the current edition is ASCE 716, so produced in 2016. ASCE 7 is produced every 6 years and go through quite a rigorous process. Wouldn't necessarily say always the best process, but a rigorous process for the updates that we have. In the ASCE 716, our biggest updates or changes to that document were a separation of our wind speed maps. We have different wind speed maps for different risk categories of our structures. We have risk category 1 or the low risk to human life. Risk category 2 are all of our buildings except for risk category 2. So risk category 3, substantial buildings that house large numbers of individuals at one time. And risk category 4 are essential facilities, hospitals, fire stations, police stations, those type of things that are there for our country. So we look at these different maps, and we've now categorized them into all those 4 different risk categories. But the biggest effort that was done by Frank Lombardo, where he looked at all of the wind speed data that we have across the United States and broke it down into thunderstorm and non-thunderstorm events for analysis. So first analysis that we've had breaking out thunderstorms and then recombining them back in and producing a map across the country that has all the hazard. What I've shown on the bottom left there is how much thunderstorms affect the map. Of course, this doesn't include our hurricane contours, which we'll add back into the map. And you can see in ASCE 710 a very uniform map across the country, where 716, the map on the right, this is for our risk category 2 structures, which are based on a 700-year main recurrence interval, has a lot more variation across the country based upon Frank's work. and then adding back in the hurricane coastline, which is for us the Gulf of Mexico and the Atlantic coast. You can see the hurricane contours there. Also, a big change for us was our roof pressure coefficients on low-rise buildings. Most of our, up until 2016, our roof pressure coefficients were based upon work done in the 70s at Upper University of Western Ontario, now called Western University in Canada. And Dr. Greg Kopp did all of this work where he looked at the different pressure coefficients that we have for the different roof zones. And you can see the solid line on the bottom there is what is currently in for the low-rise provisions in ASCE 710. And the scatters that you see for the different shown on those graphs is what Greg found in his study of the NIST database that we have for low-rise buildings. So not a very good correlation between the data and what we had in ASCE 710. And you can see as we got to the interior, it even actually got a little bit worse. The plot on the right is a plot showing that the white lines, which I know are hard to see, hopefully you can see my mouse, was our used to be our zoning that we had for the distribution of the different zones for the roof pressures. They were not good. What Greg's research showed is that our zoning needed to be improved as well. And so from that, we did increase our roof pressure coefficients. We went to the mean values as shown on the right and zoned our roofs differently. This is for the flat roof conditions. We also did the same for the sloped roof conditions and included the new roof pressure coefficients. Much higher roof pressures on the roof if you use the same wind speed as before. Of course, our wind speeds went down quite a little bit, so that helped. In 716, one of the things, you think that for all the years that we would finally, that we designed canopies on buildings, that we would have some provisions in our standard on those. We had not until 716, where we have some provisions for canopies. This is being actually even updated again in our next round for ASCE 722, which is almost ready for publication. And the one thing that we also added was for wind pressures on solar panels. That's quite a exploding industry here in the United States. And so they needed some guidance on rooftop solar and what type of roof pressures they would have on those solar panels. And so we've added that into 716. Like I said, very exploding industry in the United States. Now I want to talk just on a couple of slides about 722, which is just finishing up and should be ready by the end of the year for publication. The biggest addition, of course, to 722 is in the tornado realm. And we were adding tornadoes into our standard, which is the first time that we've ever had them. And I'm not sure about Australia. They might be the only other standard that has tornadoes within it. And you can see we have about 1,200 tornadoes per year in the US. And but the majority of them are fairly in the low, the EF0 or EF1 range, where, and like I said, almost 98% of them, 97% of them are in the EF0 to EF2 range. And so we look at them, we don't get a lot of impact from the major ones. There's very minor number of those each year, but when they do, they are devastating that we have. There are a number of fatalities that occur within each of those tornadoes. You can see, I know this graph is hard to look on this plot, but you can see the number of EF tornadoes per year, the plots there, but then how much damage is the red plot on the top, the red line on the top. So almost by the time we get past the EF1, we're all the amount of damage that we receive to our structures is fairly almost reached its max after the EF1 category. So we want to make sure that we increase our tornadoes in there. And so we have new tornado maps that will be included in 722. This is just an example of one. As you would guess, that it varies upon what the size of your building footprint is. So we call it our target size. This is a plot for a 40,000 square foot target size, and the mean recurrence interval of 3,000 years will give you these wind speeds. Now these are in miles per hour, and so you'll notice that they're lower than what we showed on the other maps, though the pressure coefficients, of course, are a lot higher for tornadoes. So we have to calculate both of them when we look at them based upon these lower wind speeds. But as the target area gets larger, of course, the wind speeds get higher as well. And for 728, just something that we're starting right now, Greg Kopp is doing a bunch of research for us to improve those 40-year-old values that we have on a series of buildings. He's done 66 buildings so far with mainly low sloped roofs. And so he's produced those studies, and you can find that on the ASCE's website, the results for that. But we're looking at much greater study to continue that work, and hopefully we'll get this funded to continue that work and include more building shapes into the study that we have, and that will greatly improve. We're trying to cut our 2 procedures that we have in ASCE 7 now down to 1, so that it's easier for everybody to calculate their wind pressures on their buildings. And finally, Chris asked me to talk a little bit about this pre-standard for performance-based wind design that was published in 2019 by ASCE. It is starting to look at performance-based wind design, because here in the United States, we do performance-based seismic design quite regularly. And for tall buildings, let's say on the West Coast, where we have high seismic loads, the wind design for the upper stories of those buildings, which usually control on a tall building, was dominating the system requirements for the seismic system down low. And so we wanted to stop that, prevent that interaction. And so we then have developed this performance-based wind design standard to look at how we would do it and allow a little bit of non-linearity into our building designs. You can read here what it's about, but really ASCE 7 is a very prescriptive standard, and this will allow the use of the performance-based design will allow for much more innovation into our building designs. We give performance objectives depend upon, again, we go back to our risk categories about what the continuous occupancy, we use continuous occupancy, operational, and occupant comfort as our different performance objectives, and define what is required for each one of those to exist. Go through this nice little flow chart that is too hard to read, of course, on the screen, but we use it to go through the different procedures to make sure that we've checked everything, the occupancy comfort, the operational performance, and then the continuous occupancy performance objectives. Gives just a guidance on how to make sure we've satisfied everything in our performance-based design. This is also gives some modeling and analysis, what you can use, whether it's approximate, elastic, static, or linear response history, or nonlinear response history analysis. It tells you which you can use for all the different performance criteria that we have on there. We've given acceleration limits for occupancy comfort, peak drift limits. We really call this DDIs, because we look at the deformation damage compatibility in that zone that we have for the different buildings. So we use that criteria to select the main wind force resisting system. And probably one of the very largest concerns that we have in performance of our buildings is in the cladding or the envelope system. And so we go into a lot of detail in our wind performance-based design standard on how to detail and install your envelope systems and what performance is required for the different objectives that you have. And so that is where we see most of our damage from buildings in the United States. And so we want to make sure that that is covered, not just the main wind force resisting systems that we have. And with that, I know we sped through a lot very quickly. I'll turn it back to Chris for questions.
Thank you very much. Thank you very much indeed, Donald. Could I ask you to unshare your screen, please?
There you go.
Could I ask all the speakers to reveal themselves